All right, so we'll get started here. Let me turn on the lights. We're kind of half in the dark. Hopefully you're, oh, thank you.
There are two, so they aren't attached.
Oh, it's okay, it's okay. No, don't even worry about the fuzzies. It's fine. I went to, I started in community college, and my community college professor used to be very, very fussy about the fuzzies, and it wasn't because of him. It was like he was teaching, and I think about like 2 years into it, his wife was like, "Enough, no more fuzzies," because he'd bring home stuff to grade, and like you got 10 students with the fuzzies, all of a sudden your house is full of the little paper nubs. But anyway. So we are, if I can find my notes. Come on. Tell me I don't have my notes. Oh. Rats. Well, I'm sorry, I won't be doing in-class exercises today. I guess they're all bonus. That's good for you, right? By the way.
Do we have to I have write everything on my notebook here, like class examples. Do I have to put them in the...
Do you prefer just to take notes on paper and not worry about my printout?
Yeah.
Okay. I mean, I don't have to, it's just this experiment this semester. If it doesn't work for you guys, we don't have to do it. I mean, you're not taking notes on my notes either, are you? You're just taking notes in a notebook, right?
Yeah.
Because you don't really, it doesn't, it's just weird.
Yeah.
Let's dispense with it then. So.
I mean, I still have them. They're all printed out and everything.
Right, but no, but.
Sometimes I transfer them over so I can see it.
But if you do, you can, I did say that if you brought them in and you had worked out in-class exercises in those notes that I hadn't worked out in here, I'd give you bonus points. So you can still do that. All right, so let's do that up to this point, and past this point, I'll just lecture. All right. I still think, though, that I will mention, those in-class examples, like those are good additional study examples. So even if I don't hit them in class, it's healthy for you to like work those out. And I may still do them if I actually remember my notes. All right. So sorry. Well, I thought I'd try it. I mean, some people lecture with like templates, and then students fill in stuff. So I was trying to find kind of a middle ground between that, because I do want students to read my notes. I can cover a certain amount in class, right? But my notes are deeper, especially with proofs and things, So let's talk about higher derivatives. So here's the definition. The second derivative of x is the derivative of the derivative of x. Other notations for this are d squared f dx squared, for example. So like the definition you can give for the nth derivative of x is defined to be the derivative with respect to x of the n minus 1th derivative. And by the way, another notation that we use in calculus is the 0th derivative of x is just equal to the function. So like the 0th derivative is just the function itself. That's the standard notation. Now we have some further terminology. If f, let's say, is a function from u to the reals, and f prime is also a function from u to the reals, and this is a continuous. If the derivative is continuous, then we say f is an element of C1u. So C1u is the set of functions which is differentiable and the derivative itself is continuous on u. All right? If you drop the continuous and you just say differentiable, you can also talk about that. You can say a function is differentiable on u if its derivative exists on u. And we can go further. If the nth derivative of f from u to r is continuous, then f is an element of Cn u. In other words, it has n continuous derivatives. All right? And then finally, if fn from u to r exists for all n, then f is an element of what's called C infinity u. So a function which is in C infinity u, this is called a smooth function. All right, a smooth function. Many of the examples that we commonly work with are smooth functions. You can keep differentiating them all day long, and you never get to something that's not differentiable. All right. So I'm going to show you today some examples of functions which are not smooth, some functions which are like have one derivative but not two. All right. So let's look at an example. See here. F of x equal to, let's say, x to the 4th plus 3x cubed plus 2x plus 8. So this is what? This is a polynomial of order 4, right? And let's calculate its derivative. So what do we got? F prime of x. We've got what? 4x cubed plus 9x squared plus 2. So that's the first derivative. We've been doing that already, right? That could have been a test 1 problem. Now we'll calculate f prime prime of x. F prime prime of x. So we've got 12x squared plus 18x. This is the second derivative of f. All right? Now we can do what? We can calculate the third derivative. So f prime 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 of x. So we got 12 times 2, which is 24, x plus 18. All right? And we can differentiate again. Now, as a matter of like common human decency, we don't do prime, 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 prime. We use the 4 notation past this point, just so like, it's just hard to read more than 3 of them, you know? So you got 24. which is a fantastically ridiculous show, by the way. Have you guys ever watched 24? You guys never, you know what I'm talking about, 24? Oh, so this was when you guys were like infants, right? So it's back in like the early thousands. It's this show, it's this counterterrorism unit show. It's about, every season is 24 literal hours. So every episode is an hour, and it covers like the events of one day. So you can imagine how ridiculous this is. The range of emotion characters go through in a single day. You know, so many terrorists tortured, all kinds of stuff like that from the George Bush years. If you guys, you really should watch the first season. It is fantastically ridiculous. It's got pretty good acting, actually. Anyway, you guys don't watch TV. What am I talking about? All right, so the fifth derivative, what do we got? What's the derivative of 24? It is a 0, right? And what happens for the sixth derivative? Nope. In fact, here, any derivative n of x is going to be equal to 0 for all n greater than or equal to 5. All of the higher derivatives past that, they're not undefined, they're just 0. Right? Just keeps going and going. So this function is an example of a smooth function because every derivative of it is a polynomial. Polynomials are continuous. So this is a smooth function on the whole real line. The domain is all reals. So actually here, f is an element of C infinity R for what it's worth. Now, I want to point out something really cool to you guys. I want to point out something really, really neat about this. All right. So check this out. What's f of 0? 8. What is f prime of 0? 2. What is f prime prime of 0? 0. What is f prime 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 of 0? Plug it in. 18, right? What's the fourth derivative at 0? 24, right? Now, Taylor's theorem says for appropriate functions, you can rebuild the function by a linear combination of, well, by a polynomial whose weights are given by the derivatives. And here's what it says. It says f of x can be written as f of 0 plus f prime of 0 times x plus 1/2 f prime prime of 0 times x squared plus 1 over 3 factorial f prime 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 of 0 times x cubed plus 1 over 4 factorial times the fourth derivative evaluated at 0 times x to the fourth, and so forth. But all the higher terms for this one are 0. Now, the 3 factorial, I know you guys might not know what that is. 3 factorial is defined to be 3 times 2 times 1. So that's actually 6. 4 factorial is 4 times 3 times 2 times 1. Although, I mean, admittedly, saying the times 1 is kind of silly, isn't it? But anyway, 4 factorial is, by definition, 4 times 3 times 2 times 1, which is, well, 24. All right? And so let's see how this works out for this example. F of 0 is 8. What's f prime of 0? It was 2. So we get 2x plus 1/2. F prime prime of 0 was 0. 1/6. The third derivative at 0 was 18. and then 1/24. The fourth derivative at 0 was 24. I'll rewrite that. So what we got is x to the fourth plus 18 over 6 is 3, x cubed plus 2x plus 8, which of course is exactly what we started with. So actually, I have a whole lab in this course that's about Taylor's theorem and exploring this idea, all right? But this gives you, perhaps this gives you some insight as to what the higher derivatives mean, all right? So like, what is the first derivative about? The first derivative is about the tangent line, right? So like the first two terms, 8 plus 2x, well, 8 plus 2x gives you the equation for the tangent line to 0 for this polynomial, all right? If you take the first, you know, the 3x cubed plus 2x plus 8, well, that's like the best cubic approximation to the polynomial at 0. But anyway, I just wanted to point this pattern out to you. I think it's interesting, and we'll come back to it, okay? So let me, ay, ay, ay. Oy. Another example. Okay, so you guys, I told you about cosh earlier in this course, didn't I? What was it? 1/2 e to the x plus e to the minus x, right? And do you guys remember what sinh was? Right? So let's see what the derivatives and the higher derivatives of these hyperbolic sine and cosine look like, right? For the sake of discussion, I'm going to call cosh f of x, all right? So what's f prime of x? Ddx of what? 1/2 e to the x plus e to the minus x. So we do what? We've got ddx. We'll factor out, pull out the 2, right? 1/2. And we got ddx of e to the x plus ddx of e to the minus x. The 2 has to distribute to both, right? Don't forget your parentheses there. Or you could write a half twice, right? I mean, it's up to you. Now the derivative of e to the x is just e to the x, right? So we get 1/2 e to the x plus e to the x, well, e to the minus x times what? Chain rule. Derivative with respect to x of minus x, right? Got to do that chain rule because we're differentiating with respect to x, but the function is of minus x. So it's not a big deal. All that ends up doing is multiplying it by -1, right? Just multiplies by -1. So what we got is 1/2 e to the x minus e to the minus x. But what's that? No, not, it wouldn't be 0, no. What is it, though? See right here? It's the hyperbolic sign. Yeah, that would be the first derivative. So the derivative of cosh, let me just put a box around it up here. Ddx of cosh x equals 2 sinh x. Unlike cosine, there's no minus, right? So hey, let's calculate the second derivative. What's f prime prime of x? So ddx of what? 1 half e to the x minus e to the minus x. So we pull out the half. We have the derivative of e to the x minus the derivative of e to the minus x, which gives us 1 half e to the x minus e to the minus x times the derivative of minus x by the chain rule. But of course, the derivative of minus x gives us a minus 1. The minus and the minus cancel, and we have 1 half e to the x plus e to the minus x, which maybe you can recognize as cosh, right? So we have this other beloved identity, ddx of sinh of x is cosh. So see, the derivatives of hyperbolic sine and cosine, they're like even easier than sine and cosine in some sense, right? There's even no plus or minus to worry about. They just circle back, you know? Okay, so like what's going to happen with the third derivative here? We're going to have ddx of what? Cosh, which is sinh. How about the fourth derivative? What's going to happen? We have the derivative of sinh, right? Because that was the third derivative. And we get cosh. So can you guys tell me how to write this, like, sort of generally? Let me set you up. If I said, what is the 2k derivative of x, what would you tell me it's equal to? And what would the 2k plus 1th derivative of x be equal to? Sinh for this one, right? Because all the, like the first derivative is sinh, the third derivative is sinh, right? But the even derivatives, like the 0th one is cosh, the f prime prime is cosh, and f prime 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 prime, 4 primes, is also cosh. So there you go. I mean, we can calculate derivatives of all order. By the way, cosh and sinh are what? These are smooth functions because, well, cosh is a smooth function because no matter how many times you differentiate it, you either get cosh or sinh, and both cosh and sinh are continuous on the reals because they're the sum of the exponential and minus the exponential, both of which are continuous, times a half. So there we go, an example. By the way, it's a good exercise for you guys to figure out things like, what's the derivative of hyperbolic tangent? How would you do that? Split up, yeah, split, exactly. Let's see here, what am I, in example 3? So this is really kind of a little bit off the beaten track, but while we're on it, so ddx of hyperbolic tangent, this is ddx of, like you were saying, sinh over cosh, right, by definition. By definition, hyperbolic tangent is hyperbolic sine over hyperbolic cosine. Sorry. Let's see here what happens. We got to do the quotient rule, right? Whew. Yowzers. So I do derivative of the top times the bottom minus the top times the derivative of the bottom. But we know how to differentiate cosh and sinh now. So it's a sinh. Sorry, horrible pun. To do this. So we got what? We got cosh cosh, also known as cosh squared x, minus sinh sinh, also known as sinh squared x. Now, it's been just long enough for you guys to forget, but what is cosh squared minus sinh squared equal to? It's equal to 1, right? So what we have here is, 1 over cosh, all squared. And that, my friends, is hyperbolic secant of x squared. So this is, I mean, come on, that's pretty cool, right? The derivative with respect to x of of hyperbolic tangent of x is hyperbolic secant squared of x. Just like we learned last class, Ddx of tangent x is not hyperbolic, but secant squared x. So there are striking similarities between the calculus of sine and cosine and the calculus of hyperbolic sine and hyperbolic cosine. Now, in terms of their application, right, the reason that hyperbolic sine and hyperbolic cosine are called what they are is because they have to do with parametrizing hyperbolas. All right? In contrast, sine and cosine play the same role for a circle. So in pre-calculus trigonometry, you learned like the unit circle has cosine theta, sine theta, right? That's actually parametrizing the unit circle in terms of sine and cosine. That's why they're sometimes called circular functions. In contrast, hyperbolic sine and hyperbolic cosine can be used to parameterize hyperbolas. Hyperbolic sine and hyperbolic cosine are also important to the mathematics of special relativity. So they have like tremendous applications in physics and so forth. Physics. We should talk about physics. Let us talk about physics. In fact, let's talk about kinematics. What's kinematics? What does this word mean? Kinematics. Kinematics is the study of motion, all right? The study of motion. Of course, the problem of kinematics is what largely motivated the discovery or invention of calculus, right? Newton wanted to use calculus to understand things like position and velocity, right? So here we go. X is position. Then v is dx dt, right? This is the instantaneous velocity. Well, let me just say it's the velocity. All right. What comes next? Well, the thing that comes next is acceleration, a. Now, a is dv dt, right? But how else could you look at this? What is dv dt? Well, if v is dx dt, see what this is? This is ddt of dx dt, right? In other words, acceleration is d squared x dt squared. So acceleration is the second derivative of the position. Do you guys know what comes past this? So have you ever been on like a train track, like an oval train track, where you go from the straight to the curved part? You know how jarring it is? Like that jarring that you feel is actually a discontinuity in the acceleration. It is a signature of what's called the jerk being non-trivial. So jerk, or J, is the next thing past acceleration. It is dA dt. So don't be a jerk. But of course, that would be the second derivative of the velocity or the third derivative of position. So, goodness gracious, sorry guys. Actually, it's not you guys I should be apologizing to, it's the people, foolish people listening on YouTube being deafened by my cough. Yeah, and I'm plumb out of, oh, wait, no, I got candy. Whew, there's hope. Let's see here, how about, so if we had x equals to x sub 0, well, let me not do that. Let's say x is equal to 13 plus t plus t cubed. All right? Find the velocity, find the acceleration, find the jerk. Can we do that? I think we can do that. So you guys tell me, what's the velocity? Can you guys tell me? Come on, you guys can do this one. 3t squared. That's part of it. Plus what? Plus 1, right? Because the derivative of t with respect to t is just 1. So that's why I get that plus 1 there. All right, guys, what's the acceleration?
Maybe
6t, very good. What's the jerk? 6, right. So now that you guys know calculus, if somebody gives you the position as a function of time, it is a simple matter of differentiation to find the velocity as a function of time, and then to differentiate again to find the acceleration as a function of time. All right? So don't be if I ask you a question about velocity or acceleration, don't mistake that for a hard problem. That's just a differentiation problem stated in different words is all. All right? Okay. Now, I think I still owe you some examples of functions which are like not smooth, right? Like, I want to show you how that can happen. So we'll just look at a couple of examples. I just want you to understand, like, not everything is smooth. Not everything can continually be differentiated forever and ever. All right, so like example 5. So let's look at f of x equal x to the 3/2. All right. What's the derivative of f? And this is going to be for x greater than or equal to 0, of course. So df dx is 3/2 x to the 3/2 minus 1, right? So what is that? 3/2 x to the 1/2. Right? Does that formula make sense? It sure does, right? This is good for x greater than or equal to 0, right? So in fact, you can see that f is certainly an element of C1 on 0 to infinity. It has a derivative. That derivative is continuous, at least one. Now let's calculate the second derivative, see what happens. What happens when we differentiate 3/2 x to the 1/2? Which, of course, we could write 3/2 square root of x, right? Well, we get 3/2 times 1/2 x to the minus 1/2, right? In other words, f prime prime of x is equal to 3 over 4 times the square root of x. Uh-oh. Now we're in trouble, right? So note f prime prime of 0 does not exist, right? Which tells me that f is not an element of C2 on 0 to infinity. All right? Now, I could say that it's twice differentiable on the set 0 to infinity. If I throw out 0, I avoid the trouble. In fact, this function's smooth if we throw out 0. But 0 is a problem. Now, can you guys tell me, like, graphically, like, what's going on here? What's happening? Help me out here. How would you graph y equals x to the 3/2? Let me suggest we make a table of values. So 0 goes to 0, 1 goes to 1. And can you tell me something else that's easy to calculate in terms of the 3/2 power? How about if we like 4? What is 4 to the 3/2? No. So that would be 4 to the 1/2 cubed, right? What's 4 to the 1/2? So the square root of 4 is 2, right? 2 cubed is 8, right? We could do 16. You know, 16 to the 3/2 is 16, the square root of 16 cubed, which is 4 cubed, which is 64, right? Okay, I think that's good. I'll put 64 out here, and I'll put, like, this will be 8. So what are we doing? We got 0. Oh, good grief, I'm wrong. This should be 16, right? Dummy. So let's see here. 0 goes to 0, 1 goes to 1, 4 goes to what? 8. And 16 goes to 64. Oh, poor choices I've made. That's like, it's like up here somewhere, isn't it? All right, anyway, it is what it is. All right, so this, roughly speaking, is y equals x to the 3/2 power, right? Now, what is the 1/2 power? By the way, what's the slope right here at 0? You can figure that out by looking at f prime of 0. So I think it should be, slope should be 0. So my graph isn't quite right. I guess it has to kind of do like this. If I'm not wrong, I don't know. That feels wrong though. It feels wrong, but anyway, the derivative, which I'll graph in green, is just 3/2 the square root function, right? So like, I'll just do the 16. 3/2 times 16 to the 1/2 power. That's 3/2 times 4, also known as 6, right? So like the square root function times 3/2 comes up to like here. And so that's something like this. So, excuse me. The trouble is that the derivative function has a vertical tangent at 0. That's why we're losing 0 at the second derivative. So like there's not a vertical tangent in the original function. Apparently it's got like a horizontal tangent at the end. All right, its derivative is 0 from the calculation we did. But when we differentiate, the next thing up it's got a vertical tangent at 0, and that's why we're losing the second derivative, because the vertical tangent means the derivative of that function is not defined. So anyway. Okay, so now that you've seen this example, could you give me a function that is like 2 times differentiable, but not 3 times differentiable at 0? Let me repeat that again. Twice, but not thrice. Differentiable at 0.
So would that mean it couldn't be smooth?
Yeah, that it wouldn't be smooth. It's true. So how about this? We do f of x equals x to the 5 halves. See, if you do f of x equals x to the 5 halves, you're going to have f prime of x equals 5 halves x to the 3 halves, and then f prime prime of x is going to be 5 halves times 3 halves x to the 1 half, and then f prime 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 of x is going to be 15 over 8 square root of x. And so f prime 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 of 0 does not exist, whereas f is an element of C2, 0 to infinity. Right? And you see you can play this game, right? You can come up with functions which you can differentiate like 10 times, not the 11th time, right? You just pick the right power. All right? So this is an example. Now the other thing you might be curious about is I've said that the derivative should be continuous. So are there functions which have derivatives which are not continuous? We've not seen one of those, okay? But here's the example. I share it with all my calculuses, so I'm sharing it with you. F of x equal to, let's see here, I think I want x times the sine of 1 over x, and this is for x not equal to 0, and f of 0 is defined to be 0, all right? So differentiate, what do you get? F prime of x is what? It's a product, right? So we got to do what? We got derivative of x with respect to x, sine of 1 over x, plus x times the derivative with respect to x, sine of 1 over x. So we get sine of 1 over x plus x times the cosine of 1 over x times the derivative of 1 over x by the chain rule. So we get sine of 1 over x. Now, the derivative of 1 over x is what? What is the derivative of 1 over x? That is the derivative of x to the minus 1, right? What is the derivative of x to the minus 1? Well, the derivative, that's minus 1 times x to the minus 2, right? In other words, it's minus 1 over x squared. Right? It's minus 1 over x squared. And so this gives you minus, so the x and the 1 over x squared gives you just minus 1 over x, the cosine of 1 over x. Now that derivative exists for x not equal to 0, right? Right. And you can actually, I'm not going to prove this, but you can show that f prime of 0 is equal to 0. All right? So this is a function which is differentiable at 0. All right? Its derivative exists at 0. But look at the formula for the derivative near 0. What does that do? What does this formula do near 0? So the sign of, I feel like I've messed this example up, but let's hope I didn't. Sorry, I don't have my notes on hand. I worry I have missed an x squared or something. Well, if I have, I'll make an announcement to you guys. It's in your notes, you know. Anybody have the notes on them? Okay. So let me graph what's going on here. So what is y equals x sine of 1 over x? So what's going on there is you're stuck between these enveloping functions of y equals x and y equals minus x, right? Because you're taking sine of 1 over x is stuck between minus 1 and 1, right? So if you think about that, the biggest this formula can be is x, and the smallest the formula can be is minus x. So it's kind of cool. It basically, the function is, I can do it. And as you're approaching 0, it's like, it's like oscillating like mad. Roughly speaking, this is the graph of y equals f of x. And so really, the derivative exists because the function is like pinching down to this, so that it does have, in a technical sense, a tangent line there, which is 0. However, in this rather perverse example, the tangent line is not a good approximation to the function there, because the function is not constant at that pinch point. It's oscillating like mad, as is revealed by this formula over here. And see, so if we were to graph the derivative, we would see something truly horrible. And it's something more like, well, more in the middle. I mean, it's chill out here. I'm doing this wrong. It's more like, this is the derivative in here. Oh man, I'm ruining my chalk. And then it kind of mellows out here, perhaps. Whatever. But well, I have graphs in the notes of this. All right. But this is this perverse example where the derivative exists, but it's not continuous. So this is an example of a function which is not continuously differentiable. All of the nicest theorems we have in calculus are for continuously differentiable functions. Continuously differentiable functions are the ones we want to usually use for models. Like if, hopefully, this is the, there are various quotes by 19th century mathematicians saying this is the sort of thing that gives them nightmares, keeps them up at night. So it ruins many of the more beautiful theorems in analysis, that example. But anyway, we can avoid that by assuming our derivatives are continuous. All right? And anyway, let us not speak of this example again. So, moving along. We have now reached implicit differentiation. Woo-hoo! So, implicit differentiation. And inverse functions You notice we haven't talked about how to differentiate like inverse sine yet? Well, we're about to do that. Now, what does the word implicit versus the word explicit mean? Do you guys know? Do you know? So let's talk about it. Explicit is when you can see it's basically just like y equals to stuff in x. This would make y an explicit function of x. It's when we can write y on its lonesome equal to an expression in x. For example, y equals to the hyperbolic cosine of x plus x cubed. There you go. This would be y is an explicit function of x. This is everything we've been doing up to this point. Implicit is when y and x are all mixed up. And basically, implicit is when you don't have y equals to just stuff in x. They're related, right? But implicitly so. So for example, you might have like x squared plus y squared equal to 1. This would make y an implicit function of x. All right? Now, sometimes when you have an implicit function, you can solve and make it explicit, right? Like this one here, you've got upstairs y equals the square root of 1 minus x squared, right? That is, in fact, this part of the circle. And downstairs, right, down here, you in fact have y equals minus the square root of 1 minus x squared. So a circle is not the graph of one function, right? It's the graph of two functions. It fails the vertical line test. But the larger point here is when y is an implicit function of x, there's a mathematical theorem which says that if you want to, you can solve for y locally. You can solve for y as a function of x if you're close to a certain point, right? This is the so-called implicit function theorem. Now, that said, we can't actually do it. That's an existence theorem. So like, it's easy to give an example where I can't do that. How about this? X squared y plus xy cubed equals to y to the 10th. Solve that for y. Right? This makes y an implicit function of x, but I cannot solve for y. All right? So we have this mathematical theory which comforts us that in principle there exists a way to solve, mathematically speaking, for y as a function of x if you pick a point which solves. But in practice we can't actually do it, right? So this is why implicit differentiation is important, because we can still implicitly differentiate such implicit relations. And through implicit differentiation, we can understand how the rate of change of y relates to x. All right? So let me show you an example. What example am I on? 8. Thank you. All right, so basically the rule is here, y is a function of x. That's the key concept. So we're given that xy plus y squared equal to x squared. All right? Goal. find dy dx. All right? Here's how it goes. We differentiate the equation which implicitly defines y as a function of x. So, but you guys already know. You already know how this goes, right? So we've got the derivative of this product, right? Plus the derivative of y squared. And on the other side, 2x, right? 2x. You're like, I got that one. So the product rule gives us dx y plus x dy dx. And the chain rule gives me the derivative of y squared is 2y. But the chain rule says I'm differentiating with respect to x, right? So I have to multiply by dy dx. Do you guys mind if I just erase that dx because it's 1? It's just 1. So our goal was to find dy dx. Can you do it? You can do it. It's just algebra at this point, right? Put all the dy dx terms on one side, put everything else on the other side. We'll do that to start with. So we've got x dy dx plus 2y dy dx equals to 2x minus y. So factor out the dy dx, we've got x plus 2y times dy dx equal to 2x minus y. All right. So what's dy dx? Right? Finishing blow. This tells me dy dx is equal to 2x minus y over x plus 2y. Now, would you guys be more likely to buy into my note-taking nonsense if it was already printed at the bookstore and you could like just buy it all together? It was like bound and nice and junk to start with, rather than like piecemeal trying to like print it out. Would that make a difference? Or is that kind of like not even an issue? Curious.
I kind of just, I take notes, and then when I do homework and stuff, I go back and look at yours
That's good.
and read through yours and mine when I do homework.
I think that's a good practice. I was talking to them before you got here about whether or not they like the format I was trying this semester, and they're both not interested. And that's fine. Like, it was an experiment. I prefer what you're saying. I think you guys taking your own notes in class and then like trying to then read through my notes and sort of synthesize those for yourself, that's a healthy process. Now, if I also had a book in addition to that, that would be annoying, wouldn't it? Because then you'd have to like notes, book, and my notes. Like,
It gets to be a lot on one table.
right. I mean, let's be honest. My notes are a book, right? I'm just missing some exercises. Does this make sense? So what's the procedure? You differentiate the equation. Every time you got a y, you pick up a dy dx. And then once you're done with that differentiation, you solve for dy dx. And the answer, you notice, it's not a function of x, right? It's implicit. See, it's got x's and y's in here. That's the nature of